Hey everyone, and welcome back to this class, Artificial Intelligence, Reinforcement Learning in Python. In this lecture, we are going to start implementing Gridworld in code. This is required for all the subsequent scripts in this course, so you'll need to understand it now. The relevant file for this lecture is gridworld.py. At the top here, we have our standard imports. Next, we have the grid class. The constructor takes in the width, height, and start position. The start position should be a tuple of two integers, and the current location will be stored in the instance variables I and j. Next, we have a setter that can set the rewards and the actions of the environment simultaneously. The actions, to be clear, enumerate all the possible actions that can take you to a new state. So for example, if there is a wall above you, you could try the action up, but you wouldn't actually go up, since that wouldn't be in the actions dictionary. The grid class will simply ignore it. So both rewards and actions will be dictionaries, where the key is the ij coordinate representing the state, and the value is either a numerical reward or a list of possible actions. You'll see later that the actions will be represented by the strings u, d, l, and r. Next, we have the setState function. This function will be useful for the various algorithms we'll be using. For example, iterative policy evaluation requires us to loop through all the states and then do an action to get to the next state. In order to know what the next state is, we have to actually put the agent into that state, do the action, and then determine the next state. We don't automatically have a master list of state transitions. We need to figure them out by playing the game. Next, we have the current state function. This tells us the current ij position of the agent. Next, we have the isTerminal function. This returns a boolean, true if the argument s is a terminal state, false if not. An easy way to determine if we're in a terminal state is to check if the state is in the actions dictionary. If you can do an action from the state, then you can transition to a different state, and if that's the case, then your state is not terminal. Next, we have the move function. This takes in the action as an argument. The first thing the function does is check if the action is in the actions dictionary. If it's not, then we can't do this movement on the grid, so we simply stay in the same position. Otherwise, we do the action. Note that if we follow array conventions here, so I is 0 at the top and increases downward, j is 0 at the left and increases going right. At the end, we return the reward for the current position from the rewards dictionary. The current position can be a new position after taking the action, or it can simply be the same position if the action that was passed in did not result in any movement. Note that if there is no reward defined for this position, the default is just 0. Next, we have the undo-move function. The idea is you would pass in the action you just did, and the environment will undo it. So if you just did up, it'll move you back down. At the end, there's a sanity check to ensure that the current state is in the set of all allowed states. The code should never reach this point, which is why we put an assert here. Next, similar to the tic-tac-toe game, we have the game over function, which returns true if the game is over and false if not. In this scenario, game over is much easier since all we need to do is check if we're in a terminal state. Lastly, we have the allStates function, which we used earlier in undo-move. We can calculate all the states simply by enumerating all the states from which we can take an action, which don't include terminal states, and all the states that return a reward, which do include terminal states. Since there might be some states in both the action keys and the reward keys, we cast it to a set. This also makes the data structure an O of 1 search. Next, we have the standard grid function, which returns what I'll refer to as the standard grid. This is a grid that has the reward structure I showed you earlier, with +1 reward at the top right and -1 reward underneath it, and both of those are terminal states. All the actions are defined such that we can move within the grid but never off it. We also can't walk into the wall, nor can we walk out of a terminal state. Next, we have the negative grid function. The idea behind this is that we want to penalize each move. Recall earlier when we talked about solving a maze. We said that a robot that just moved randomly would eventually solve the maze, and if you only gave it a reward for solving the maze, then it would never learn anything beyond a random strategy. We learned that we could incentivize the robot to solve the maze more efficiently by giving it a negative reward for each step taken. And so that's what we're doing here. We're incentivizing the robot to solve the maze efficiently rather than moving randomly until it hits the goal. You'll see in the code examples how these two reward structures can affect the policy that the agent eventually learns.